Okay, so today we have Ahmed El-Guindy, and he's going to be talking about some l-adic properties of modular forms with nebentypus and L-regular partitions.
Okay, thank you very much for the invitation. It's a pleasure to be here virtually. And I'd like to talk about this topic, which is a joint work with Mustafa Ghazi, a student of mine who just finished his master's degree and is now working on his PhD. And this was part of his thesis. So uh, we're going to define the things that appear in the title. So let me get into that. Right. So you're probably familiar with the concept of partition of an integer, which is the number of ways of writing it as a sum of non-negative integers. The order doesn't matter. And then there are many variants of this concept of partitions. So one of them is what are called k-regular partitions. And k-regular partition is where we count the ones only that are where the number of parts is not divisible by k. So none of the parts is divisible by k. And we denote that by bkn, and the kind of by convention bk of 0 is 1. And if you think about the generating function for this, then it's simply it will be the product of 1 minus q to the mk divided by 1 minus q to the m. So essentially the denominator kind of counts all the regular partitions. If I only had 1 in the numerator, then this will just count the standard partitions. But having this 1 minus q to the mk in the numerator kind of cancels the ones where they have any parts that are divisible by k. And one famous example kind of this function is when k is 2, because then that's exactly the number of partition into odd parts. So none of the parts are divisible by 2, so we're only counting the partitions into odd parts. And there is a very famous theorem by Euler, which is kind of one of the first thing one proves in the theory of partitions, is that if this partition into odd parts is equal to the number of partition into distinct parts. And kind of one way to see that is looking at this generating function and noticing the formula that I have written there, that 1 minus q to the 2m over 1 minus q to the m is 1 plus q to the m, and that's exactly the number of partition into distinct parts. And so that's one of the things. But now you see where we have a lot more freedom with different values of k. You can take 3 regular, 5 regular, any L regular. And if we think about the behavior of this function, then we notice that for small values of n compared to k, it's the same as the standard partitions, the ones where you count just without any restrictions, because there can be no parts that are equal to k for these small numbers. But once we reach k, we start removing some of them. So for example, at k itself, we have the number of partitions minus 1. At k plus 1, also the same thing, minus 1, because there can only be one partition where the parts are k. At k equals k plus 2 is the number of partitions minus 2, because now we remove the partition k plus 1 and k plus 2, and so on. So we can build kind of for specific values, we can kind of relate bk to pk. But in general, there is no obvious relation. Obviously, as you get bigger, these kind of obvious things stop being so obvious, and you get the regular complications of working with the theory of partitions. And so the connection with modular forms, essentially, this is a talk about modular forms, and kind of the partitions is really just an excuse to bring them into the picture. And so we have the famous Dedekind eta function, which has this definition, which plays a very central role in the theory of partition. And again, the Pn are related to 1 over eta of z, essentially without the q to the 1 over 24. And it has a weight which is equal to negative 1/2. And the bk, on the other hand, by the formula that we showed, are related to, with a little bit of a correction factor as well, related to kind of the q that appears in the beginning, is related to eta of kz over eta z, which is a weight zero. And not only weight zero, but also has properties which are related to the level and character as we will talk about them more. So, there is a shift in the type of partitions that we're studying, but also in the background, there's a shift in the type of modular forms that we're studying. For instance, kind of to motivate why one would be interested in such partition, why put these restrictions? So on the one hand, there's this concept of like looking at how the modular form changed. That's one of the reasons we put such restrictions. But here there's also a more intrinsic reason related to irreducible representations. So if we look at the representation of the symmetric group into Z mod L, then actually BLN is the number of such representations. And on the other hand, P of n itself is the number of such representations in characteristic zero. So it has a more natural interest in it, this function. And indeed, it's a well-studied variant. It's by no means something that we introduced. It was introduced a very long time ago. And people studied their divisibility properties, kind of similar to what we're doing. And broadly speaking, like there are two types of things that they studied, either mod L itself, like so the same L regular and mod L, but sometimes also people study like, let's say 3 regular, but mod 13 or something like that. You can do like different primes. But for us today, we're kind of mostly focused on the case where the K itself and the L are both the same. And, previously, most results were kind of limited to specific primes. So like, 5, 7, 11, 13, 17, 19, and so on. What we will prove today is a theorem that's actually true for all primes greater than or equal to 5. Although it takes, for smaller primes, it's simpler, but there is a statement for all primes. And here is kind of one statement, which is simpler for the smaller values. It says that if L is a prime between 5 and 31, then there is a certain bound, which we're calling BL of M, such that for integers that are of the same parity, either both even or both odd, and which are bigger than that bound, then within that range, we see that the L regular partitions on a certain sequence, okay, is congruent to a certain constant multiplied by the BL at another sequence. So now I'll show you an example in a few slides kind of to clarify this, but it's really a statement on, there this B1 of n here and B2 of n. They're really, the two expressions are very similar. One of them is with B1 and one of them is with B2. And the point is that, these are different numbers at different powers of L, and yet they are congruent modulo multiplication by a certain constant that's kind of fixed. It depends on the B1 and the B2. And it's not a congruent modulo just one L. It's actually a family of infinite congruences, because for every power of L, I just change the constant a little bit and I get a similar formula. Moreover, when we're in the range 5, 7, 11, this constant is actually 0. So which then means that all of these coefficients are divisible by L to the M within these sequences. But then for other values, we get positive values for the constant. So this is one statement, and I'm going to clarify it with an example. So here's an example. In the case of L is equal to 17, we see that the formula holds for essentially all integers with the same parity. So there is no, the bound that we need to start working at is actually just the beginning. And for example, the constant then when we put the B at 1 and 3 is 11, and we have this formula. So if we look at B17 at this value, it's congruent to B17 at this value, okay, for all n. And then we're gonna get a different value for the constant if we start looking at congruence mod 17 squared, and a different value of the constant if we look at mod 17 cubed and so on. This constant changes, but then everything else is the same. Okay. And so these results actually generalize similar results for the standard partition function by Folsom, Kent, and Ono back in 2012. And actually, it was expanded on by work of Boylan and Webb. And again, kind of going back to the modular point of view, what's really going on is we're kind of almost taking a square root of their argument in a sense. One way of looking at it is the forms that we work on are essentially half the weights of what they did, and they have characters whereas theirs didn't. So that's kind of the technical aspects that are going on in the background. But the general structure of the argument is similar. Modulo taking care of these technical issues. Now, as I said, we have a statement that's more general that works for all primes, not just for the ones between 5 and 31. And essentially, it comes by viewing that statement as one where we're looking at a certain module of rank 1, essentially proving that a certain module has rank 1 and hence forcing these congruences. And for other primes, we can still prove that the relevant module has finite rank and even bounded. And so we know that within a certain range, the rank will be 2. Within a certain range, the rank will be bounded by 3, and so on. And so, we could write more elaborate versions where we have a linear combinations of things, not just a single constant. So in order for us to state this, let me kind of recall some notation. So essentially, we want to attach to each prime an integer, which is really just one of a finite list. So it's something mod 24. And depending on whether L is within a certain range, then it will be one of those. We can write a fancy formula for it, but that's essentially, we can also as easily just state that these are these numbers. And we're going to define kind of a modified generating function for the partition, for the L regular partitions. So, later on, maybe a few slides down the road, I'll show you kind of a more intrinsic way of looking at this function. But for now, this is just a definition that, here's a generating series, and I'm just picking up specific values of the L regular partitions and multiplying them by Q to the n over 24. And, these are essentially the same values that appeared in the theorem, so it's not very surprising. And of course, as a standard convention, whenever this number is not an integer, then we put the L of alpha to be 0. Otherwise, it is whatever we get. And we know, for instance, that L squared is always 1 mod 24, and so we have these two congruences. And based on them, we can determine when this expression is an integer exactly. And so we can restate the formula for BL as this sum. Okay, so this is just an equivalent way of stating it using the congruences for L squared and L2 odd numbers. Okay, and so we have this kind. This function will play an important role throughout the rest of the talk. We also have this other function, which is just coming as a certain eta quotient. And we also have the U operator, which applied to a power series kind of just focuses on the coefficients where the exponent is divisible by L. So it only kind of isolates these exponents. And then it divides the exponent by L. So that kind of becomes another function. And this preserves modular forms, as we will see. So I think this is hopefully the last technical part here, is that we now define another sequence of integers, of functions, of modular functions, where our first one, the 0th term, is a certain eta product. So it's eta of LZ, okay, or prime L, and then multiplied by eta of Z to the C minus 1. That was the constant I defined a couple of slides ago. And now the corresponding statement for the work for the standard partition function that I mentioned they actually just started with 1 at this point and then applied the same operators that we're kind of applying down here. But for us, 1 wasn't good enough. We had to kind of start with something a little bit trickier. But kind of once we found this, then we kind of did what they do is you start with this. This is R0, and then R1. You take this function, multiply it by this power of this phi L to the C, and apply the U operator. And then so this defines R1, and then R2 is you then apply the U operator again without multiplying by phi. And then R3 is you take R2 multiplied by phi and apply the U operator. And R4, you apply the U operator again. So this is kind of a sequence where you kind of keep either hitting the previous function by UL, kind of applying the U operator and just identifying the coefficients that are divisible by L, or the exponents and their coefficients, or you multiply by this function, which kind of mixes the coefficients a little bit. And we'll see why this is a natural or a useful thing to do. I cannot claim it's natural, but it's useful. Okay. And what we end up getting then after kind of going through these technicalities, which are straightforward, there is nothing really deep here, it's just computations, that the function that we defined, the BL, which if you remember encoded the L regular partitions, are essentially very much related to these RLs, which are kind of defined by this weird multiplying by phi and applying U a number of times. So essentially, they are these BLs multiplied by a certain power of eta, either eta L of Z or eta Z, depending on whether B is even or odd. And the interesting thing is that this kind of takes us squarely into the modular form territory. So these RLs starting from R0 is clearly a modular form, and phi is a modular form. And so the product is modular form, and applying UL preserves modularity, preserves characters and everything. And so that's why we kind of know that BL is up to division by eta of LZ or eta Z is a modular form. So this is kind of the idea of the proof is kind of relating the regular partition functions to a class of modular forms and then essentially working on them, transferring the problem into that domain. Multiplying by phi L kind of raises the level, but then applying U brings it back to L. So that's kind of one of the reasons for kind of making these operations useful for us. And as I said, maybe from this point of view, we see that the coefficients of BL, the way we defined them, if I go back, it was a definition that seemed weird at the beginning. Kind of now maybe it makes more sense that essentially it's the part that remains when we isolate the eta of LZ to the C or eta of Z to the C from this process to the RLs. Okay. People could disagree and say that the first definition is more natural, or is that neither of them is natural, but at least one of them is useful, as I hope to show you. So any questions so far? Okay, so moving on. So now that we have these RLs, we're gonna build from them two infinite families of modules. Okay. So the odd family will be the ones which is spanned by the odd RLs, starting from the whatever bound we have here. Okay, so there is an index for the family, and so if B is, let's say, 0, so then we'll be taking all of them. If B is 1, then this will be 3 here, and we're starting from 1 and so on. So the odd one and the even one is similar. The odd one is spanned by an infinite number of these RLs as a module over Z mod L mz. So we also have a free parameter m that we can move independently of the B's. But the first one is spanned by all of them. The second one is spanned by all of them except the first, and the third one is spanned by all of them first two, and so on. So that's why we're calling them a descending family of modules, because there is clear containment. First one contains all of them, and then they get smaller. and similarly for the even ones. Okay. So as defined, they are infinitely generated. Okay, they're generated by an infinite number that even if we throw away a few of them, we're always throwing away a few at the beginning, okay, and keeping the rest. The next theorem that we're going to state, we show that they're actually finitely generated. In fact, the very first statement, the very first theorem that I showed you a while ago, the one that was for L between 5 and 31, essentially was stating that this module is of rank 1, because essentially it said that all of them are multiples of each other in the cases where L is between 5 and 31. So even though initially it's infinitely generated, I only needed one, in fact, in this case. And in general, we will show that they're finitely generated. So here is the statement. So it says that after a certain bound, this sequence stabilizes, and so even though I'm using I'm kind of throwing away some of the things, I remain constant in the generators, and not just that, but it's bounded above the rank of the module. The stabilized module is bounded above by this quantity here, which is easy to compute. And in fact, if we compute it in the cases where L is between 5 and 31, we'll see that it's less than or equal to 1. And likewise, the even sequence stabilizes. And furthermore, when it stabilizes, it will actually be isomorphic to the odd sequence. Now, keep in mind that they're generated by different forms. The RLs for even values are different from the ones for odd values, but there's still an isomorphism between them. That's the statement of the second. Okay. And the sketch of the proof here is that even though RL, if you remember, RL was the one defined as eta of LZ times eta of Z to the C, even though it has a level and a character in its modular space, it is actually congruent modulo powers of L to a cusp form of much higher weight. So there is this phenomena that we'll actually discuss a little bit more in a few slides, where modular forms, even though if they are in spaces where there is a level or a character, they tend to be congruent to modular forms on the full modular group, but on different levels. On different weights. The weight usually goes higher. And it goes higher with M as well. So mod L, it will be a certain number, but mod L squared, it will be higher and higher. But there is this phenomena of l-adic convergence, essentially. And so we start for this formula, we had the statement for RL0, and we can actually generalize it to any RL of BZ, that there will be a certain space of level 1 modular forms where it's congruent to, and this value will depend on the power that I want. So if I wanted mod L, I have this particular value, and for higher powers, we get this. There are a couple of exceptions that kind of, in some of the small cases, 5 and 13 and things like that, which I just won't state for the sake of simplicity. With if you're interested, I can share with you the paper afterwards, which has all the details. And so these congruences imply that actually the space kind of obtained by reducing these cusp forms, mod L kind of is an overspace for the sequence that I showed you, let's say for the odd ones. And so this is kind of excellent because we have this connection now with level 1 modular forms. And this kind of by looking at the dimension of the space and being a Z mod L M module, then it's finite. And so being finite, then we must have some stabilization after a while with this within this sequence. and kind of that's essentially the main idea of the proof. I mean, there are some technical details, of course, and I'll maybe mention a few of them, but kind of that's the sketch in general, that we kind of embedded this whole sequence into a space where we know it's finitely generated. And kind of the dependence here is on indeed on this KLM, which does grow, but for a fixed M is fixed. And so that's why we get the finiteness of this picture here. Okay, and then furthermore, so you see in principle, this shows stabilization, shows finiteness, but it doesn't necessarily show the bound on the rank that we mentioned, because these, as we mentioned, these keep growing as a function of J or of M. Okay, these numbers, of course, are very high powers of L to the J multiplied by other things. But in fact, we can actually prove that there is an injection between this stabilized module and a space where, so you see this left-hand side does depend on M, but the right-hand side doesn't. Okay, so they all kind of inject in the same space in a way that preserves the order of vanishing and preserve the congruences. And so kind of that's how we can actually obtain the bound in the theorem, which was independent of M. Okay, so this is kind of something interesting, that not just does this stabilize, but maybe for different M's, but in fact the bound is the rank is bounded above by something that's independent of M. Okay. So as I said, there are lots of technical details. The paper is about 19 pages. As I said, I'll be more happy to share it. But some of the tools that we use are things called filtrations, congruences, and twisted trace. So maybe I'll show you a few details about them in the next slide. So filtration, kind of, I already alluded to them in a way, is that this phenomena of having a modular form with L integral coefficient congruent to another modular form of level 1, say. Sometimes you can even do it between different levels. Let's say level 2n and level n or something like that. But for us, it will be level 1 for purposes of this talk in general. And so we define the filtration of a modular form to be the least integer for which such a congruence can take place. We know that, for example, there is the Eisenstein series of weight p minus 1 is congruent to 1 mod p, which means that if I take a modular form mod p and multiply it by the Eisenstein series, then I will increase the weight by p plus 1 and change the coefficients because it's congruent to 1. So I have some freedom in the choice of weight, but this process will increase the filtration. So I take the minimum one, the one that I cannot go any lower. Okay. And there is a well-known fact that if f is congruent to G mod L and G is of weight K, then the filtration has to be congruent to K mod L minus 1. So this is kind of, in some sense, a converse of what I just said. Multiplying by E sub L minus 1 will change the weight by minus 1. And what this is saying is that the weight cannot change by anything else. It will have to be multiples of L minus 1. So once I have the equivalence class mod L minus 1 of the weight, then that cannot change. The actual weight can change, but then the filtration, as we mentioned, is the smallest among them. And so here's, for instance, an interesting lemma, which shows that the filtration kind of behave in a somehow controlled fashion. For instance, under the action of the U operator. So you see, if I have a form, just actually any power series with L integral coefficients, and it is congruent to some modular form, so that kind of will give us that it has a non-zero filtration. Then if I act on this function by the U operator, I get another thing that has a filtration. and the filtration is bounded by this quantity. And generally speaking, this quantity is less than the filtration of F itself. So if I have a form with big filtration and then I apply the U operator, what this here is saying is that it will tend to go down. That's kind of one of the important tools we use in the proof to control these spaces and their congruences to the other spaces of modular forms of level 1. And so kind of based on that, we apply the UL operator and the DCL. The DCL is this, remember we had this even case and odd case. The DC was the one that appeared in odd case. I actually defined it in the talk, but apparently later than this slide. I thought I defined it the first time it appeared, but it appears here as well. So this was the one where we multiplied by phi and apply the U. So we want to show that both of them decrease the filtration. And so here's a lemma in that direction. So it says that if I have power series, which is congruent to a non-zero modular form, in particular, if it has a filtration, and if KL is this number, which kind of appeared on a number of previous slides already, and we're kind of making this assumption, which is the only case that we actually need for this talk. We can, we have do more general things, but this is kind of the most natural thing for our purposes, that if the filtration of L kind of falls in this particular equivalence class mod L minus 1, okay? This will be true of the functions RL of 0 and RL of B and so on. So this is the case that we need. And you see the statement then is that if my filtration is already less than or equal to KL, this value here, then applying the U operator takes it to be within this bound. Okay. And applying the X operator, which I don't believe I defined, the X operator is the D and then the U. Sorry about that. I should have had a little bit more notation here, but I just said it. We'll take it back kind of within the same range. So we have, all these operators that we're dealing with, and we're kind of what we're doing here is we're kind of prescribing what each one of them does within certain bounds. So if I have this bound here for F, then I get kind of this. This is really kind of relatively very small. Okay, it's just half L minus 1 plus C over 2. This is just additive. This one is a little bit bigger because C can be big. So multiplying by it will make it a little bit bigger. But kind of essentially moving by U or by X kind of keeps us within these ranges. If, on the other hand, the second part, if I have this instead for L, then again, applying the D will keep it within the range with the K. And then if it is bigger than this, then applying the X will always bring it down. And so since it always brings it down, that eventually I'll be in the case where I can apply 1 or 2. So if I start with something that's bigger than this range, then I can just keep applying until I bring it down. And then once I'm down into this range, I can make use of these lemmas. Okay. Let me say maybe something about the proof. So there was this lemma of Sayre that I told you what it does to the general U action. We said it's going to be less than or equal to L and then plus something. And so we then just apply straightforward these formula, and we get this value here. And we also note that we have the congruence that's relating the valuation of L to the valuation of f of UL mod L minus 1. And kind of here's where we use the particular equivalence class that we have. And essentially, we just look for the maximal positive integer within that bound that satisfies the congruence. And then we get the number that appeared in the statement. So it's really kind of a straightforward verification once you know the theorems that apply for these cases. And then for the second part, sorry, I seem to have misplaced the second part. Well, it's similar. So, without getting into too much details, I think it's probably underneath in the slide. So, but I think it's technical anyway, but you kind of get the gist of the idea from here, that essentially we're applying, um, we're applying this lemma kind of by noticing how if I know the value of the valuation here, and I substitute and I get certain simplifications, then I can start saying things within certain ranges. That's essentially the idea of the proof of the three parts. Okay. And then lastly, kind of in the way of technical details, um, it's easy to see that whenever I have a congruence mod L, I can lift it to congruences mod L to the J, simply by taking the appropriate powers. And so some of our work will start by doing something mod L and then lift it just using this. Okay. So here, let me kind of bring things a little bit more concretely by showing you examples of all these phenomena. So as we said, we have RLB, which was, to remind you, eta of LZ times eta of Z to the C. So it is a form of weight C over 2. And if you remember, C had like a finite list of values. And so C over 2 will also have a finite list of values, some of them even, some of them odd. It is a form of this weight of level L and of quadratic character. And the point that we were making about filtrations and so on is that it will actually be congruent to things that are of level 1. And so here's a very concrete example. If I look at R23 1 Z, then it's congruent mod 23 to delta squared times eta. Okay. And in this case, if you substitute in the formulas that we had, then we get something like KL equals 34. Now, on the other hand, you see, I'm looking at still the same left-hand side, R23 1Z, but now I'm raising the congruence to be mod 23 squared. And now I get a more complicated form and a higher weight. Okay, and that's typical of what happens here, that as I increase the kind of the accuracy of my approximation p-adically, then the weight goes higher. And you see it goes high very quickly. And already at congruences mod 23 cubed, I get this kind of enormous weight for the right-hand side. But the important thing is that it's all level 1. And kind of the surprising thing, which is predicted in some of our theorems, is that even though the right-hand side is a space of huge dimension, only a relatively small number of terms appear. And so this comes from the bounds that we have on these ranks and so on. Okay, and the fact that we said that there's kind of this low weight where everything can inject into it. So we have these examples, and we can build examples for any other prime as well. Okay. And so this is essentially kind of encapsulates the idea of filtration and what we saw in the previous slide. Now, let me actually close with something that's a bit tangential, but it was actually used in an important way in the proof. And when studying it, I noticed some interesting phenomena, which I believe it should be classical and well known. Probably it is. Maybe some of you can tell me more about it. But when I saw it, it was a nice phenomenon the first time I see it. So essentially, because we have all these characters hanging around, we sometimes need to multiply by certain functions that essentially play a role similar to EP minus 1. So remember I said that EP minus 1 or EL minus 1 is congruent to 1 mod L. And we kind of want modular forms with character that has this phenomena, and essentially it's these that do the trick. So these are level L modular forms. We're going to specify to a specific weight which has nice congruence properties, but there is a pair of them now that appears because essentially we have two cusps. So they are defined in this manner. This is very similar to the definition of the standard Eisenstein series, except that we have generalized Bernoulli numbers relative to the character that we have. And the sum is kind of twisted by this character as well. So the usual Eisenstein series we have just dk minus 1 here, but here we're twisting by chi of d, which, for example, will eliminate certain divisors, the ones where chi of d is 0. And for some of them, they'll have a positive sign. For some of them, they'll have a negative sign. And as I said, they actually come naturally in pairs, these Eisenstein series, unlike the level 1 case as well, where there was only this one Eisenstein series in each weight. Here they come in pairs. And the second one has a Q expansion, which looks very similar, except that instead of taking chi of D, we take chi of N over D. Okay. And here is the formula that I was telling you about, that if we take the weight L minus 1 over 2, okay, then we get that this Eisenstein series is congruent to 1 mod L. And this is very similar to the EP minus 1 being congruent to 1 mod P. And if you remember to the very beginning of my talk, or maybe not the very beginning, but early enough, I mentioned how we're kind of essentially taking the square root or taking half the weights of the forms that appear in when working with level 1. And that's an example of this happening. This form here has half the weight of that essentially. But in addition to that, in addition to this function and the role it plays in filtration and everything, they also have this symmetry that I'm going to show you in the next slide. So if we look at this Eisenstein series, we have this constant term that's coming from the generalized Bernoulli numbers and so on, and then we have this expansion. And if you notice the expansion here, we have some plus signs, some negative signs. They're kind of predicted by the character. And we also have kind of a self-symmetry within the expansion. So if you just look at the first one, you notice that this Q of 7, if I apply the U operator, then it will become this Q. And then the Q to the 14, it's the same as the coefficient of Q squared. The Q to the 21 is the same as the coefficient of the Q cubed, and so on. And all of this can be proved actually by using the formulas here. So I'm not saying that this is unprovable or anything, but it's nice to see. And then there is a question after that. And if you look at the F, and even though the definition is a little bit different, so we're doing chi of N over D, not chi of D. But then what happens is essentially you get, for the coefficients which are not divisible by 7, you get the same absolute values. So this business with the sign changing disappears. These are all positive, okay, which I don't believe is obvious from the definition, but provable. And then we also have something funny going on with the coefficients that are divisible by 7. And you can probably guess what it is, because it's kind of similar to what's happening here, but multiplied by 49. So if we divide this by 49, we get this Q to the 7, which is related to this Q that appears here. If we multiply this to 245 by 49, then we get this 5 to the Q14, and so on. And here, this will give us the positive 8, not the negative 8, because now we don't have these negatives, and so on. So this was a curious phenomenon when I saw it. And as I said, on the one hand, it's provable, so it's not mysterious in that sense. And it kind of not just happens for this example, it happens for all of them. My question, I guess, which I'm gonna essentially close with, is whether this appears elsewhere, or whether this can be useful in proving things. It just looks so pretty in my eyes, at least. And so we can kind of state it a little bit, kind of having these relations between the different F and the different E's. And it looks like some kind of fractal phenomena where within the same modular form, it reappears a number of times. Okay, so within this modular form, we have itself appearing again, and similarly here. So with this, I finish my talk, and I thank you very much for your attention.
Thank you, Ahmed. Are there any questions?
Thank you, Ahmed. It was a very nice talk.
Thank you, Ilhan. Thank you very much, and thank you again for the invitation.
Uh, so the Z mod L and Z module structure that you introduced in your slides, do they have some other extra algebraic properties? They satisfy interesting properties, maybe.
So for us, we were only interested in the question of finite generation and of kind of the bounds on the rank. But as
So,
you say, there could be more interesting properties, of course.
so it is like when you pass to the intersection, the odd module and the even module, they end up to be the same, you said, right?
Isomorphic.
Isomorphic, yeah,
Yeah, because
I
they're
see.
generated by different forms. So they look different, but
I
when they
see.
stabilize, they're isomorphic.
Oh, well, that's quite interesting, actually.
Mhm.
And do they have some representation theoretic property, maybe?
Yeah, that would be an interesting question.
Yeah,
We didn't study it, it was kind of a tool to kind of reach the formula. But yes, I think I agree that they merit kind of their own study.
right. Yeah, thank you.
Thank you. Any other questions?
Stop the recording now.